What is reliability?
Industrial engineers use another type of statistical technique called reliability. A system that always produces the same results and that hopefully meets or exceeds its specifications. A product is analyzed using the reliability function, or survivor function. The probability of a unit in a system that does not fail in a certain specified time interval. If the unit does fail in a system, it means the end of the unit's ability to perform the required function. This is determined by the failure distribution function, or the probability of an item failing in a specific time interval. Calculations involving the common failure rates of various mechanical devices often results in a graph with a bathtub-shaped curve.
What is reliability?
Industrial engineers use another type of statistical technique called reliability. A system that always produces the same results and that hopefully meets or exceeds its specifications. A product is analyzed using the reliability function, or survivor function. The probability of a unit in a system that does not fail in a certain specified time interval. If the unit does fail in a system, it means the end of the unit's ability to perform the required function. This is determined by the failure distribution function, or the probability of an item failing in a specific time interval. Calculations involving the common failure rates of various mechanical devices often results in a graph with a bathtub-shaped curve.
How is mathematics used to enable buildings to withstand earthquakes?
It is not usually the quake that kills people, but the collapse of structures. In particular, the horizontal shaking during a quake is mostly responsible for causing building or road damage and collapse. Most structures are designed to carry heavy loads, so they are strong in the vertical direction. Designing structures to withstand the horizontal earthquake shaking can save buildings and lives. There may be other ways to mitigate the amount of structural collapse. During quakes, all include a healthy dose of simple and complex mathematics. One expensive way would be to design all buildings to withstand the largest ground shaking an area can expect. This could be done using mathematics familiar to designers and engineers. The math involved analyzes how large quake frequency waves travel through an area. Yet another, more practical, solution might be to design buildings to withstand the specific types of shaking expected in a region. Again, mathematics could be used to determine the frequency at which each building vibrates, or the number of times a building sways per second, versus the potential type of quakes that roll through the area.
What is fluid mechanics?
Fluids are substances that flow, including gases and liquids. Fluid mechanics, or hydraulics, is the study of the physical behavior of these gases and liquids and their role in engineering systems. This includes the mathematics of the forces in and motion of substances, turbulence, wave propagation, and so on. Most fluid mechanics problems in engineering are mathematically modeled using differential equations. These models can also be applied to other engineering areas, such as electromagnetism and the mechanics of solids, because solids still move, albeit slowly. Other fluid mechanical studies include the compressibility of substances. In most cases, liquids are considered to be incompressible and gases are considered to be compressible. But there are exceptions in some everyday engineering applications, and they can easily be explored using mathematical modeling. Engineers also use special mathematical equations to determine certain characteristics of fluid flow, such as whether the flow is slow and smooth, laminar, or turbulent. For example, the ratio of inertia forces to viscous forces within a fluid can be expressed by what is called the Reynolds number. Laminar fluid flow can be described by the Navier-Stokes equations. For no viscosity, or an ideal flow called inviscid flow, the Bernoulli equation can be used. Finally, when the flow is zero, or static, the fluid is governed by the laws and equations of fluid statics.
What is the heat index?
Our bodies dissipate heat by varying the rate of blood circulation, losing water through the skin and sweat glands and, as a last resort, by panting when the blood is heated above 98.6 degrees Fahrenheit. 37 degrees centigrade, the average body temperature. Sweating cools the body through evaporation. You can get the same feeling when you put alcohol on your skin, because as the alcohol evaporates, the skin is cooled. The heat index, HI, is an index that combines air temperature and relative humidity to estimate how hot it actually feels. It is based on a mathematical concept called the heat index equation, a long equation that includes the dry air temperature, relative humidity, in percent form, and many biometeorological factors too long to list here. The resulting heat index table represents the apparent, or feels like, temperature. For example, if the air temperature is 90 degrees Fahrenheit, with the relative humidity at 60%, it will feel like 100 degrees Fahrenheit.
How do civil engineers use mathematics?
Although most civil engineers actually spend only a small portion of their time doing calculations, mathematics is essential to this field. For example, civil engineers may use math to carry out the technical calculations in order to plan a construction project. They may use math to model and simulate the possible behavior of a structure before it is actually built. They also use math to understand the necessary chemistry, the strength of a material, and/or physical components, how strong parts need to be, of a construction project.
What is reliability?
Industrial engineers use another type of statistical technique called reliability. A system that always produces the same results and that hopefully meets or exceeds its specifications. A product is analyzed using the reliability function, or survivor function. The probability of a unit in a system that does not fail in a certain specified time interval. If the unit does fail in a system, it means the end of the unit's ability to perform the required function. This is determined by the failure distribution function, or the probability of an item failing in a specific time interval. Calculations involving the common failure rates of various mechanical devices often results in a graph with a bathtub-shaped curve.
How much does air pressure decrease with altitude?
It takes mathematics to figure out how much air pressure decreases with altitude. Close to the surface, and due to the pull of gravity, the air pressure exerted by air molecules is greatest, around 1000 millibars at sea level. From there, it declines quickly with altitude to 500 millibars at around 18,000 feet, 5,500 meters. At 40 miles, 64.37 kilometers, it will be 1/10,000 th of the surface air pressure. This can also be interpreted another way, for altitudes of less than about 3,000 feet, 914.4 meters. The barometric air pressure decreases about 0.01 inches of mercury for each 10 feet, 3 meters of altitude, or a decrease of 1 inch of mercury for each 1,000 foot 304.8 meters gain in altitude. If millibars are used, it is 1 millibar for every 26.25 foot, 8 meter, altitude gain. That means if a person takes a ride in an elevator, hits the button for the 50th floor and coincidentally has a barometer in his or her pocket, the pressure would fall by approximately 0.5 inch, 1.27 centimeters, during the ascent. This also means that higher altitude cities have major differences in barometric readings. For example, the air pressure in almost mile-high Denver, Colorado, is only 85% that of cities that reside at sea level.
Why do meteorologists want people to pay attention to the heat index?
The major reason involves how the body responds to high heat value numbers. If the relative humidity is high, it curtails evaporation on the skin, and the body is unable to effectively cool itself, and a person will perceive that the air is warmer. When heat index values grow higher, conditions exceed the level a body can remove heat, causing the body temperature to rise. This can cause heat-related illnesses, such as sunstroke or heat exhaustion. For example, according to the United States National Weather Service, exposure to direct sunlight can increase the high by up to 15 degrees Fahrenheit, 9.4 degrees centigrade. And when a heat index between a mere 90 degrees Fahrenheit, 32.2 degrees centigrade, to 105 degrees Fahrenheit, 40.6 degrees centigrade, can cause possible sunstroke, heat exhaustion, and heat cramps. It is easy to see the meteorologist's concerns. The following table shows how the heat we actually experience changes with temperature and humidity. Humidity is expressed as a percentage, temperatures are in degrees Fahrenheit. According to the National Weather Service, sunstroke, heat cramps, and heat exhaustion are possible above 90 degrees Fahrenheit. Temperatures above 105 degrees can also lead to heat stroke, and above 130 degrees heat stroke is likely if exposure to such temperatures is prolonged.
How are absolute and relative humidity determined?
Like many other facets of meteorology, mathematics comes in handy when determining absolute and relative humidities. The absolute humidity is the mass of water vapor divided by the mass of dry air in a specific volume of air at a specific temperature. In this instance, the warmer the air, the more water vapor it contains. On the other hand, relative humidity, RH, is the ratio of the absolute humidity to the highest possible absolute humidity, which in turn depends on the current air temperature. Mathematically, RH is often defined as the ratio of the water vapor density, mass per unit volume, to the saturation water vapor density, usually expressed as a percent. The equation for relative humidity is RH equals actual water vapor density / vapor saturation density x 100%. More commonly, RH is thought of as the amount of water vapor in the air at a given temperature in comparison to the amount that the air could contain at the same temperature. For example, if an area is experiencing 100% relative humidity, that usually means the air is saturated with, can't hold any more, water vapor.
How is mathematics important to electrical engineering?
There are many branches of mathematics that are important to electrical engineering. For example, abstract math is used in communication and signal processing. Complex differential equations solving equations involving derivatives are used in circuit theory and systems design. Also in circuit theory, engineers need to know algebra and trigonometry. Engineers who deal with electromagnetism need to know calculus, especially Maxwell's equations. For more about Maxwell, see Math in the Physical Sciences.
What are some examples of mathematical models used by chemical engineers?
There are numerous examples of how mathematical models are used by chemical engineers, too many to mention them all here. One good example is modeling crystal growth. Liquids from water to molten metals become crystalline solids as they are cooled. Engineers can mathematically design software that helps in the manufacture of superior crystalline growth, especially for electronics and other industries. These improved crystal forms advance the quality of electronic hardware, including computers, and help engineers design better alloys for a wide range of applications.
How do surveyors make measurements?
Most of a surveyor's measurements are gathered with a theodolite, an instrument that acts as a telescope, ruler, and protractor. The theodolite is set up over a known spot, such as a previously surveyed corner of a lot. Its telescope then sights a specific spot, such as another corner of a lot, and the distance is measured. Most modern theodolites use lasers to measure distance, supplemented by angular measurements in both the horizontal and vertical planes. The surveyor then uses trigonometry to analyze the data, converting it to a more usable form, usually in x, y, and z coordinates. For example, depending on the desired outcome, the vertical angle and slope distances can be converted from polar measurements to show differences in elevations and horizontal distances. The horizontal distances and angles can also be converted from polar measurements to rectangular coordinates. For more about coordinates, see geometry and trigonometry.
How is air density related to air pressure?
The expression thin air is actually a reference to the atmosphere's density, or how thick the air molecules are near the Earth's surface. In chemistry terms, density is merely the mass of anything, including air, divided by the volume the mass occupies. For example, the density of dry air at sea level is high, mainly due to the pull of gravity. In metric system terms, sea level density is about 1.2929 kg/m3, or about 1/800 th the density of water. But as altitude increases, the density drops dramatically. Mathematically speaking, the density of air is proportional to the air pressure and inversely proportional to temperature. Thus, the higher up one is in the atmosphere, the lower the air pressure and the lower the air density. There is somewhat of an athletic advantage to higher elevations at least for players of such sports as football and baseball. Because the air density is lower, a ball thrown in high elevation places like Denver, Colorado, will travel even farther than a ball thrown in a close to sea level city, such as Miami, Florida. In fact, the air at the Denver Stadium allows balls to travel almost 10% farther.
How is math used to understand chemical reactions?
One of the simplest examples of mathematics used in understanding chemical reactions is based on two chemicals, A and B. They can be molecules or ions. If A and B encounter one another, they can rearrange themselves into molecules or ions of two other substances, in this example, C and D. The reaction that takes place can give off or absorb energy, making the molecules move faster or slower. Although this is a simple example of what can happen in a chemical reaction, it can still be analyzed using mathematical modeling.
How is mathematics used to determine resistor values in an electrical network?
Electrical engineers who deal with systems and circuit theory need to know the terms and functions of the basic circuit element resistor, capacitor, and inductor in terms of current voltage associations determined by impedance, obstruction, complex numbers, calculus, and Laplace transforms, see above, are all mathematical concepts used to understand circuit theory. The best way to understand the basics are through the following simple equations. Resistor voltage equals current, I, times resistance, R, or V equals IR. Capacitor voltage equals the square root of -1, J, often called I, or an imaginary number, times frequency. W, times the capacitance, C, all times the current, I, or V equals, JWC, I. Inductor voltage equals the current divided by the square root of -1, J, times frequency, W, times inductance, L, or V equals I/JWL.
How do surveyors use mathematics?
Surveyors use mathematics, especially geometry and trigonometry, because they need to measure angles and distances on the ground. They then interpret the data, accurately plotting such information as boundaries and locations of structures on a map. These maps are then used for personal or legal means, such as a survey of a person's lot showing ownership boundaries in order to obtain a mortgage. The traditional method of surveying is called plane surveying, which does not take into consideration the curvature of the Earth because, for most small projects, this curvature doesn't really matter. When it does, especially for projects measuring greater distances, the method used is called geodetic surveying.
How are imaginary numbers used in electrical engineering?
Imaginary numbers are used in electrical engineering because complex numbers are an integral part of electrical problems. In fact, there are often more imaginary numbers in electrical engineering problems than there are real numbers. This is because a complex number is a pair of numbers in which one number is real. The other imaginary, or a real number multiplied by the value I, defined as the square root of -1. For more information about imaginary numbers, see Math Basics. For instance, we know electricity flows through an electrical circuit component such as a light bulb. The bulb actually resists the flow of some electricity by doing work or shining thus. The current is real and measured by a current meter. But if the current can't flow through a device, the current becomes imaginary. For example, a capacitor is two pieces of metal that do not touch. Therefore, if one adds a voltage, no real current can flow through it.
How is math used in statistical process control?
Statistical process control, SPC, involves using statistical techniques to measure and analyze the variations within a process. With SPC, industrial engineers monitor, control, and ideally, improve a process through statistical analysis. The four basic steps include measuring the process, eliminating variables within the process to make it consistent, monitoring the process, and finally, improving the process to make the, usually better, intended product. But it is not the answer to everything. All the SPC does is ensure that the product is being manufactured and designed as intended. Thus, SPC does not tell whether the design is good or bad, just if it's made according to plan.
How is air temperature measured?
Simply put, there are two ways to look at air temperature, on the microscale. It is the small-scale measure of gas molecules' average kinetic energy. On a larger scale, it is the action of the atmospheric gases as a whole. In physics, an entire branch is devoted to objects' temperatures and the transfer of heat between objects of differing temperatures. Called thermodynamics, it is a study that entails a great deal of mathematical knowledge. No matter what the type of temperature discussed. The most common apparatus for measurement is the thermometer. The most familiar thermometers are thin, long, closed glass tubes containing some type of liquid, most often alcohol or mercury. When the temperature increases or the air around the tube heats up, it causes the liquid to expand, moving it up the tube. Air temperature measurements are most commonly read in centigrade or Fahrenheit. For more about centigrade, Celsius and Fahrenheit, see Mathematics Throughout History.
How is barometric, or air, pressure measured?
Barometric, or air, pressure, named after the instrument used to measure this pressure, is caused by the weight of the atmosphere pressing down on the land, ocean, and air below, with gravity creating the downward force. Because pressure is dependent on the amount of air above a certain point, pressures are greatest at the surface and less at higher altitudes. On the average, at sea level, the air has a pressure of 14.7 pounds per square inch. A 1-inch square has 14.7 pounds of air pressure on each side. The United States National Weather Service does not measure pressure in pounds per square inch, but in terms of inches of mercury, or how high the pressure pushes mercury in a sealed tube. Air pressure aloft is reported in millibars, or hectopascals HPA. A term most often used by scientists to measure air pressure. Most of us are very familiar with air pressure as it changes with the weather. For example, the use of the terms high pressure system and low pressure systems are often indicators of the types of weather fronts traveling through a region. In general, falling air pressure, seen on a barometer, means that clouds and precipitation are more likely. Rising air pressure means that clear weather is more likely. In addition, many people experience personal changes in air pressure. For example, the discomfort or even pain felt in a person's ears as they ascend or descend in an airplane. A large hill, or even in an elevator, is evidence of changing air pressure.
How is linear algebra used to determine the stability of structures?
Structural engineers use linear algebra a great deal, mainly because there are numerous equations with many unknowns associated with the analysis of a structure in equilibrium. Most of the time, these equations are linear, even when bending, material deformation, is involved. Linear algebra can also be used for other structural concerns, because it deals with the study of vectors. Vector spaces, linear transformations, and systems of linear equations. Of course, linear algebra is not only used to understand structures. Almost every subfield in engineering uses these types of mathematical calculations. For more about linear algebra and linear equations, see algebra.
What is the new formula used for calculating wind chill?
Most people know about wind chill, the temperature your body feels when it is exposed to a certain air temperature combined with a particular wind speed. The higher the wind speed, the colder the wind chill temperature, and the faster the exposed areas of a person's body will lose heat, a process known as transpo-evaporation. When moisture evaporates, the surface from which it evaporates loses some heat. The newest wind chill chart, called the wind chill temperature index, took over from the old chart. Developed in 1945, in the 2001 to 2002 winter season. The reason for the change was simple: the original wind chill index revolved around heat loss. With a standard set at the chill experienced while standing outside in air moving 4 miles, 2 kilometers, per hour. Based purely on temperature and wind and on how water freezes in plastic containers, the charts were developed in Antarctica by Paul Sippel and his fellow explorer, P.F. Passel. Back in 1939, partly with the intention of being used in World War II battlefield planning. Not everyone was thrilled with this simplistic, two-factor interpretation, however. There were pieces missing from the wind chill puzzle, such as the fact that humans constantly generate heat to the lack of wind measurements above 40 and below 5 miles per hour, 64 and 5 kilometers per hour. Passel and Sippel's wind speeds were also taken about 33 feet, 10 meters, above the ground, making the chart more valuable for a third-floor office than ground level. But the biggest problem overall was that the old wind chill chart could not accurately predict how humans perceive temperature. Thus, the new wind chill index was created. This chart includes such changes as wind speeds calculated at the average height of a human head, about 5 feet 1.52 meters above the ground. It is based on a human face model and sundry other more modern considerations. The actual general formula for the wind chill has now changed to the following. Wind chill in degrees Fahrenheit equals 35.74 plus 0.6215 T 35.75, V 0.16, plus 0.4275, V 0.16. In which T is the air temperature, in degrees Fahrenheit, and V is the wind speed, in miles per hour. The biggest difference between the old and new indexes is that the new index usually registers warmer temperatures than the old index. Still, no matter what the equation or chart, when temperatures are icy cold and winds are high, everyone should be careful and bundle up.
How are studies of fluid mechanics used today?
The list of engineering uses of fluid mechanics in the modern world seems endless, and no wonder, since it is one of the most widely applied areas of mathematics and engineering. Some of today's uses of fluid mechanics in various fields include: understanding the movement of molten liquid, rock, or lava, in volcanic eruptions, studying the flow of air over objects to help design airplanes, the space shuttle, and even spacecraft that fly through the atmospheres of other planets. Airflow studies in the automobile industry to design cars with more aerodynamic profiles, analyzing the ups and downs of the stock market. Examining natural hazards, such as snow conditions that result in an avalanche. Interpreting turbulent flow in sewer and water pipes, and in river channels. Studying complicated flow of weather patterns in the atmosphere, researching the effects of gravity, and other waves in space. And using fluid mechanics applications to study the deep oceans and coastal shorelines, including waves and currents.
Is math used to describe the strength of materials?
Materials science is also a major part of engineering, and includes a great deal of mathematics. For example, engineers need to know how materials stand up to stress and strain from the pressure of either a structure or overlying materials. A basic understanding of how structures respond to the action of forces and how these forces affect the performance of various building materials, such as wood, steel, concrete, and so on, is essential.
Are advances in technology fundamental to our understanding of materials?
Yes, advances in technology are truly fundamental to our understanding of materials, and vice versa. For example, transistors and superconductors were developed by understanding the mathematics of the materials that make up these objects. Math and materials science together have also advanced technology used in infrastructure, such as highways and overpasses, aerospace, such as satellites and shuttles, and microelectronics, such as those found in automobiles. Today, the need to describe material behavior resulting from physical interactions is forcing scientists to develop new mathematics. In fact, materials science has evolved to the point in which researchers from physics, engineering, and applied mathematics are working together on common problems.
How is mathematics used in chemical engineering?
Mathematics is used a great deal in chemical engineering, especially since chemical engineers design materials and the processes by which those materials are made. To solve chemical problems, many types of mathematics are used, not least of which is calculus, including partial differential equations. Even simple calculations, such as working on chemical formulas and equations, involve mathematics. For more information about chemical formulas and equations, see Math in the physical sciences. Traditionally, chemical engineers worked in the petroleum and large-scale chemical industries. More recently, they have spread out to the pharmaceutical, foodstuff, polymer and material, microelectronics, and biotechnology industries. Using mathematics, they are involved in such studies as thermodynamics, chemical reaction processes, and process dynamics, design and control. They help to develop new chemical products and processes, test processing equipment and instrumentation, gather data, and monitor quality. Chemical engineers also build mathematical models and analyze the results, mostly to help understand the performance of a process. In fact, the solution to a math problem is often in the understanding of the behavior of the process described by the mathematics, rather than the specific numerical result.
Why do weather reports sometimes say the humidity is 100% when there is no rain or snow falling?
A reading of 100% humidity usually means there is a high probability that rain will be or is occurring, but not always. It might be 100% RH because clouds are forming. If the RH near the ground is much less, for example, if a relatively dry air mass is in place, there will be no rain at the surface. This is why Doppler radar sometimes shows rain or snow in an area when none is actually reaching the ground.
How is math used to calculate the pressure behind a dam?
There are many engineering considerations and calculations needed when building a dam. The most important being the water pressure behind the structure. Engineers know that as the elevation of water behind a dam increases, the height and density of the water causes higher pressures at the bottom of the dam. Thinking in mathematical terms, the horizontal force acting on the dam is the integral of the water pressure over the area of the dam that is in contact with the water. The force exerted by the water pushes horizontally on the dam face, and this is resisted by the force of static friction between the dam and the bedrock foundation on which it rests. The water also tries to rotate the dam about a line running along the base of the dam. The torque resulting from the weight of the dam acts in the opposite sense. For example, take the water pressure on a dam, such as the Hoover Dam on the Colorado River between Arizona and Nevada. Before building that dam, engineers needed to know the pressure not only along the entire structure, but also and especially at its base. In general, the pressure exerted by water equals the density times the depth, in which the density of water is 62.4 pounds per cubic foot. For Hoover Dam, this gives a pressure of 37,440 pounds per square foot, or 18.72 tons per square foot. The pressure calculated at half the height of the dam is 9.36 tons per square foot. This is why the base width of the dam is 1,660 feet, 201.2 meters. It is thicker to compensate for the increase in pressure at the bottom of the dam, while the width of the crest of the dam is only 45 feet, 13.7 meters.
What is architecture?
Simply put, architecture is the design of structures, mainly buildings, by architects. but the definition does not end there. An architect not only builds the structures, he or she also takes into consideration the form, symmetry, spaces, and beauty of the building. In order to do this, mathematics is needed to work out such building factors as angles, distances, shapes, and sizes.
What is the composition of the air?
Meteorologists determine the composition of air by analyzing its various constituents. These are mainly displayed in terms of percent of the atmosphere. The first 40 to 50 miles, 64 to 80 kilometers above the surface contains 99% of the total mass of the Earth's atmosphere. It is generally uniform in composition, except for a high concentration of ozone, known as the ozone layer, at 12 to 30 miles, 19 to 50 kilometers, in altitude. In the lowest part of the atmosphere, the area in which humans, other animals, and plants live, the most common gases are nitrogen, 78.09%, oxygen, 20.95%, argon, 0.93%, carbon dioxide, 0.03%, and minute traces of such gases as neon, helium, methane, krypton, hydrogen, xenon, and ozone. Water vapor is also present in the lower atmosphere, although variable and at a very low percent. Higher in the atmosphere, the composition and percentages change as the atmosphere thins. For more about percents, see Math Basics.
How old is the study of fluid mechanics?
According to many historians, fluid mechanics may be the oldest subfield in physics and engineering. In particular, ancient civilizations needed to control water flow for agricultural development, drinking water supplies, and transportation. Thus, the development of fluid mechanics, which is the study of the motion and behavior of fluids, led to even more, and complex, improvements. For example, agricultural requirements led to irrigation waterways, dams, weirs, pumps, and even crude forms of sprinkler systems. The need for a potable, drinkable, water supply led to better wells, fountains, and water storage systems, and water transportation innovations included improved sails and rigs, as well as methods to build and waterproof sailing vessels. But early fluid mechanical studies did not end there. Over time, they extended into almost every realm of science and engineering. For example, mechanical engineering uses fluid mechanics because of the need to know about fluids used in combustion. Ships and automobiles, lubrication, from the smaller inner workings of a wheel to larger mechanisms such as locks along a canal, and energy systems, hydroelectric power. Civil engineering utilizes fluid mechanical studies to interpret how fluid systems traveled over structures. Aqueducts and pipes carrying drinking or waste water. Electrical engineers use fluid flow to analyze how to cool electronic devices with either air or water. Even early, and current, aeronautical engineers needed to know how air flowed over an airplane wing, providing the much-needed lift that allows a plane to become airborne.
How are millibars converted to inches of mercury?
Mathematically, the conversion is simple. The air pressure at sea level is 29.92 inches of mercury, or 1013.2 millibars. For example, if you see air pressure of 1016 millibars on a weather map, convert to inches of mercury by multiplying by 29.92, and then divide by 1013.2. The result is 30.00 inches of mercury.
What is the world's longest suspension bridge?
Ten years after construction began, Japan's Akashi Kaikyo Bridge, also known as the Pearl Bridge, was finally opened on April 5, 1998. It is the longest suspension bridge in the world. Stretching 12,828 feet, 3,910 meters, across the Akashi Strait to link the city of Kobe with Owajishima Island. Its main span length, or center section, which is the way world's longest status is determined, reaches 6,532 feet, 1,991 meters, between support columns. The span length is almost a quarter mile longer than the previous record holder, the Storebælt. Great Belt East Bridge, in Denmark, which also opened in 1998. But this bridge may eventually lose its top dog status. The Italian government has approved plans to begin building what will be the longest suspension bridge in the world between mainland Italy and Sicily. It will be quite an engineering feat, with the main span stretching just over 10,827 feet, 3,300 meters. Interestingly enough, Japan and Italy are known to be tectonically active, with both receiving more than their fair share of volcanic eruptions and earthquakes, as well as, in Japan, tsunamis.
What is statistical quality control?
Quality control has been around for a while in a crude sense. When a certain product was manufactured, and consumers chose that product, the makers would try to improve the quality of the product or lower its price. The improvement of the quality did not stop with the product, but also included the process for making the product. But the use of mathematics was minor in early quality control. It was not until the 1920s that statistics was applied to industry and quality control, mainly because of the development of sampling theory. For more about sampling, See Applied Mathematics. Modern statistical quality control refers to using statistical techniques for measuring and improving the quality of processes. It is often broken down into statistical process control, SPC, see above, and statistical quality control, SQC. Both terms are usually used interchangeably, although SQC has a broader focus than SPC. To compare, SPC is the application of statistical techniques to control a process, reducing variation so that performance remains within specific limits. SQC is the application of statistical techniques to control quality and includes acceptance sampling, inspection of a sample from a lot to decide whether to accept that lot, as well as SPC.
How is wind measured?
Wind speed is the measurable motion of air with respect to the surface of the earth. It is measured in terms of a unit distance over a unit time, such as miles per hour. The wind direction is also an indication of the wind's source. For example, a southerly wind means the wind is blowing toward north. It is coming from a southerly direction.
How are statistics used in industrial engineering?
Industrial engineers study the efficient use of personnel, materials, and machines in factories, stores, repair shops, and offices. They prepare layouts of machinery and equipment, plan the flow of work, make statistical studies, and analyze production costs. In particular, they rely heavily on a branch of mathematics called statistics and probability. For more about statistics and probability, see Applied Mathematics.
Who was Oliver Heaviside?
English electrical engineer Oliver Heaviside, 1850 to 1925. Was a self-taught genius who made several contributions to the field of electricity and even atmospheric studies. In 1902, Heaviside predicted that there was a conducting layer in the atmosphere that allowed radio waves to follow the Earth's curvature, a layer now named after him. In electrical engineering, Heaviside was best known for operational calculus, a tool for solving linear differential equations with constant coefficients. It was usually applied to brief or fleeting, called transient phenomena, and was very similar to Laplace transform in its calculations. Although Laplace had developed his ideas almost a century before, Heaviside knew nothing of them, because they were not well known during his time. But Heaviside's operational calculus did have its problems, as well as its critics. It was severely limited because of its lack of mathematical theory. This not only limited its applications, but also created many uncertainties and ambiguities in the equations and solutions. Today, operational calculus has been replaced by Laplace transform, especially in fields such as electrical engineering.
What is the bathtub curve?
Industrial engineers usually know about the bathtub curve, especially in reference to an operating or failing unit. In other words, if enough units from a given population are observed operating and failing over time, it is relatively easy to compute week by week, or month by month or year by year, estimates of the failure rate. The results of the calculated population failure rates over time produces a graph. Because the shape of this failure rate curve resembles the end-to-end section of an antique bathtub, it is widely known as the bathtub curve. This type of analysis is usually used in industrial settings. For example, it can describe the expected failure rate of certain electronics over time. Initially high, then dropping to zero failures for most of the system's lifetime. Then rising again to the other end of the tub as the electronics tire out.
What is the bathtub curve?
Industrial engineers usually know about the bathtub curve, especially in reference to an operating or failing unit. In other words, if enough units from a given population are observed operating and failing over time, it is relatively easy to compute week by week, or month by month or year by year, estimates of the failure rate. The results of the calculated population failure rates over time produces a graph. Because the shape of this failure rate curve resembles the end-to-end section of an antique bathtub, it is widely known as the bathtub curve. This type of analysis is usually used in industrial settings. For example, it can describe the expected failure rate of certain electronics over time. Initially high, then dropping to zero failures for most of the system's lifetime. Then rising again to the other end of the tub as the electronics tire out.
What is an aerospace engineer?
Aerospace engineers are directly involved with putting objects from airplanes and the space shuttle to deep spacecraft into the sky and beyond. Using sundry mathematical models and techniques, they install, construct, maintain, and test systems used to launch, diagnose, or track aircraft and space vehicles. They may calibrate test equipment and determine causes of equipment malfunctions. Using computers and communication systems, aerospace engineers often record and interpret test data.
What is an aerospace engineer?
Aerospace engineers are directly involved with putting objects from airplanes and the space shuttle to deep spacecraft into the sky and beyond. Using sundry mathematical models and techniques, they install, construct, maintain, and test systems used to launch, diagnose, or track aircraft and space vehicles. They may calibrate test equipment and determine causes of equipment malfunctions. Using computers and communication systems, aerospace engineers often record and interpret test data.
What is orbital mechanics?
Orbital mechanics, also called flight mechanics, is the study of the motions of artificial satellites and space vehicles moving under the influence of forces such as gravity, atmospheric drag, thrust, and so on. It is a modern spin-off of celestial mechanics, or the study of the motions of planetary and celestial bodies. One of the main scientists who built the foundations of orbital mechanics was mathematician Isaac Newton. 1642 to 1727, who put forth his laws of motion and formulated the law of universal gravitation. For more about Newton, see History of Mathematics and Mathematical Analysis. For more about Newton's laws, see Mathematics in the Physical Sciences. Today's aerospace engineers apply orbital mechanics to such problems as rocket and spacecraft trajectories, re-entry and landing of space vehicles, rendezvous computations, such as the Space Shuttle to the International Space Station, and lunar and interplanetary trajectories for manned and unmanned vehicles.
What is orbital mechanics?
Orbital mechanics, also called flight mechanics, is the study of the motions of artificial satellites and space vehicles moving under the influence of forces such as gravity, atmospheric drag, thrust, and so on. It is a modern spin-off of celestial mechanics, or the study of the motions of planetary and celestial bodies. One of the main scientists who built the foundations of orbital mechanics was mathematician Isaac Newton. 1642 to 1727, who put forth his laws of motion and formulated the law of universal gravitation. For more about Newton, see History of Mathematics and Mathematical Analysis. For more about Newton's laws, see Mathematics in the Physical Sciences. Today's aerospace engineers apply orbital mechanics to such problems as rocket and spacecraft trajectories, re-entry and landing of space vehicles, rendezvous computations, such as the Space Shuttle to the International Space Station, and lunar and interplanetary trajectories for manned and unmanned vehicles.
How do engineers determine the escape velocity of a rocket?
A ball thrown into the air will rise and then return, thanks to the Earth's gravity. If the ball is given a larger initial velocity, it will rise even higher and then return. With even more velocity, the ball will reach a certain escape velocity, in which the ball escapes the gravitational pull of the planet. If the ball is launched with an initial velocity greater than the escape velocity, it will rise and not return. In this case, physicists say that the ball was given enough kinetic energy to overcome all of the negative gravitational potential energy, or it launches into space. Thus, if m is the mass of the ball, m is the mass of the Earth, g is the gravitational constant, v is the velocity, and r is the radius of the Earth, then the potential energy is equal to gmm/r. The kinetic energy of the launched ball is equal to mv2/2. This is independent of the mass of the ball. To see how this works to an aerospace engineer, just replace the word ball with space vehicle.
How do engineers determine the escape velocity of a rocket?
A ball thrown into the air will rise and then return, thanks to the Earth's gravity. If the ball is given a larger initial velocity, it will rise even higher and then return. With even more velocity, the ball will reach a certain escape velocity, in which the ball escapes the gravitational pull of the planet. If the ball is launched with an initial velocity greater than the escape velocity, it will rise and not return. In this case, physicists say that the ball was given enough kinetic energy to overcome all of the negative gravitational potential energy, or it launches into space. Thus, if m is the mass of the ball, m is the mass of the Earth, g is the gravitational constant, v is the velocity, and r is the radius of the Earth, then the potential energy is equal to gmm/r. The kinetic energy of the launched ball is equal to mv2/2. This is independent of the mass of the ball. To see how this works to an aerospace engineer, just replace the word ball with space vehicle.
Why were counting devices developed?
Early counting devices were developed for a logical reason: to allow people to count items in order to trade or to keep track of stock, such as cattle. They also used simple counting devices to keep track of the seasons, mostly for agriculture, in other words, to know when to plant, and for religious reasons, such as marking days for certain feasts. For more about counting in ancient times, see History of Mathematics.
Why were counting devices developed?
Early counting devices were developed for a logical reason: to allow people to count items in order to trade or to keep track of stock, such as cattle. They also used simple counting devices to keep track of the seasons, mostly for agriculture, in other words, to know when to plant, and for religious reasons, such as marking days for certain feasts. For more about counting in ancient times, see History of Mathematics.
What were some early counting devices?
The very earliest counting devices were human hands, with the fingers used as digits. There were limitations to this device, though, especially since each hand only has 5 fingers. To count more items, some cultures assigned even larger counts to other parts of the body. Such counting methods became tedious, so merchants and others who needed to keep track of assorted items turned to nature, using sticks, stones, and bones to count. Eventually, devices called counting boards were developed. At first, the counting boards were simple, usually entailing drawing lines with fingers or a stylus in the sand or dirt.
What were some early counting devices?
The very earliest counting devices were human hands, with the fingers used as digits. There were limitations to this device, though, especially since each hand only has 5 fingers. To count more items, some cultures assigned even larger counts to other parts of the body. Such counting methods became tedious, so merchants and others who needed to keep track of assorted items turned to nature, using sticks, stones, and bones to count. Eventually, devices called counting boards were developed. At first, the counting boards were simple, usually entailing drawing lines with fingers or a stylus in the sand or dirt.
What are the oldest surviving counting boards?
To date, the oldest surviving counting board is the Salamis tablet. Discovered in 1846 on the island of Salamis, it was once thought to be a gaming board. But historians have since determined that the white marble slab was actually used to count items. The tablet, which measures 59 inches, 149 centimeters, in length, 30 inches, 75 centimeters in width, and is 1.8 inches, 4.5 centimeters, thick, was used by the Babylonians around 300 BCE. It contains 5 groups of markings, with a set of 5 parallel lines equally divided by a vertical line in the center. Below that is a group of 11 parallel lines, all divided by a perpendicular line. But this was not the only counting board of that time. After the Salamis tablet was developed, the Romans brought out the calculi and the hand abacus around 300 BCE to 500 CE. These counting boards were made of stone and metal. One example of a Roman abacus had 8 long and 8 short grooves arranged in a row. Beads would slide into the grooves, indicating the counted units. The longer grooves were marked I to indicate single units, X to indicate tens, and so on up to millions. The shorter grooves were used to indicate multiples of 5, 5 units, 5 tens, and so on. There were also shorter grooves on the right side of the abacus. which were probably used to indicate Roman ounces and for certain weight measurements.
What are the oldest surviving counting boards?
To date, the oldest surviving counting board is the Salamis tablet. Discovered in 1846 on the island of Salamis, it was once thought to be a gaming board. But historians have since determined that the white marble slab was actually used to count items. The tablet, which measures 59 inches, 149 centimeters, in length, 30 inches, 75 centimeters in width, and is 1.8 inches, 4.5 centimeters, thick, was used by the Babylonians around 300 BCE. It contains 5 groups of markings, with a set of 5 parallel lines equally divided by a vertical line in the center. Below that is a group of 11 parallel lines, all divided by a perpendicular line. But this was not the only counting board of that time. After the Salamis tablet was developed, the Romans brought out the calculi and the hand abacus around 300 BCE to 500 CE. These counting boards were made of stone and metal. One example of a Roman abacus had 8 long and 8 short grooves arranged in a row. Beads would slide into the grooves, indicating the counted units. The longer grooves were marked I to indicate single units, X to indicate tens, and so on up to millions. The shorter grooves were used to indicate multiples of 5, 5 units, 5 tens, and so on. There were also shorter grooves on the right side of the abacus, which were probably used to indicate Roman ounces and for certain weight measurements.